our channel Euclid Mathematics. We have started a lecture series on CSIR NET SET Gate and other competitive exam too. So already I started lecture series on a ring theory. So already we learned most of the concept from ring theory. Now in my today's video, we are going to learn what from ring theory, which is a commutative ring, Boolean ring, zero divisor with some of the example. So now in my today's video, we are going to learn the topic which is from ring theory, which is a commutative ring. So the definition of a commutative ring, it says that, okay, already we learned the definition of a commutative group. Okay, so commutative group, it says that when we have A star B, which is equal to B star A, okay, such a type of the operation, then we say that the group hold that commutative property. Okay, so group need to satisfy A star B, which is equal to B star A. So similarly, we have to apply this property for commutative ring. Okay, so only the difference is here we learn about the group. Now in my today's video, we're going to learn about the ring. Okay, so the definition of a commutative ring, it says that when we have the element A and B and A, their product is equal. Okay, so the definition is here, a ring R under addition dot is said to be a commutative ring. So when we said it is a commutative ring, when we have AB which is equal to BA, and this both A and B which is coming from the ring. Okay, so now let's get to see some of the example. So here first example I took it here, ring as a M2R, that means a matrix over 2 by 2 is a commutative ring. So we have to check that whether it is a commutative ring or not. Okay, so as we know that if we take matrix like 1 by 1 matrix, it is always commutative. But if we go for 2 by 2 matrix, 3 by 3 matrix, or n by n matrix, product of first two matrix which is not equal to the product of second and first matrix. Okay, so like AB which is not equal to BA, so matrix multiplication it is never get equal AB which is equal to BA. So that's why orally we can say that the matrix it is not commutative when we have 2 by 2 matrix. Okay, so if it is not commutative for 2 by 2, similarly it is applicable for 3 by 3, 4 by 4 and n by n matrix. So the matrix when n taken greater than or equal to 2, then matrix multiplication it is a not commutative. Okay, so it is not commutative. So similarly here I have taken over R. Okay, so instead of that you can go for Q or C or Zn modulo n or Zi or Zni. Okay, so you may check it for these one also. Now so in my next example I will explain here the Q cross R. Okay, the cross product of Q cross R is commutative or not. Okay, so how we can prove the cross product of a two Q cross R is commutative or not. Okay, so we know that Q rational it is commutative, always commutative ring. Real it is also always commutative ring. So for your understanding or for verification, take some counter example like any element from AB from that group itself and show their commutative property hold. Okay, so for Q rational, real, complex, Zn modulo n, Gaussian integer Zi, Zni are always commutative ring. Okay, so it is quite easy to find out whether it is commutative or not. Okay, so you just have to select some of the counter example in order to prove these are commutative or not. Okay, now here we go through one of the example which is a cross product of a two group. Okay, so like a Q cross R, and we have to show that Q cross R is a commutative ring. Okay, and we know that to show any group is a commutative ring. Okay, so we have to take the two elements from it and prove that element of a first two product which is equal to element of a second into first product. Okay, like A B which is equal to B into A, so star hold operation there. Now consider any element. So Q here means it contain any element like a 0, non-zero or any type of the element, and R also it contains 0, negative, positive, all type of the element. So for our solution I taken here first element AB from A from Q and B from R, so it is coming as an order pair because we have cross product, so always we are getting order pair. So first A from Q and B from R I taken here, and second element Y CD, C from Q and D from R. Okay, so X and Y it is from our ring Q cross R, and we have to show that X dot Y which is equal to Y dot X, then we say that our R Q cross R is a commutative ring. Now let's find out whether it is equal or not. Okay, so here X dot Y means I consider first element AB dot Y is a CD, so AB dot CD. Now multiply this order pair. So how we multiply order pair, how we add and how we subtract, I already explained in my previous lecture. Okay, so we have to go through only corresponding elements. So here the first corresponding element with respect to A to C and B to D. So we have to multiply first element with the first. So A dot C comma B dot D. Okay, so we can write AC as a CA. It doesn't matter because Q and R, this type of the group always hold this property. Okay, so in Q we can write A cross B, which is equal to B cross A. Okay, this hold in Q. Okay, similarly, so we write here CA and BD as a DB. Now again get reverse from our order pair CA and DB. So CA first corresponding element with respect to C is a D here. So CD here, and second corresponding element A and B here. Okay, now so I got the again two order pair back. Now we can observe here, it seems like that CD, it is having value Y and AB having value X. Okay, so X dot Y, which is equal to Y dot X. So when this property hold, then we say that our QR ring is a commutative ring. Okay, Q cross R is a commutative ring. Or you may go through, first of all, find out X dot Y, then find out Y dot X, and prove these both are equal. Okay, it is quite easy to prove. So nothing is difficult on it. Okay, so I hope so you all have understood this one. So it is very quite easy example. So this type of the example are very much important to get our definition and this concept more clear. Okay, so similarly you may try for your homework Z cross Q, Z cross Z, Q cross Q, Q cross C, Q cross R cross C. Now I taken here three order pair. Okay, three group Q cross R cross C. So we have to select two elements like A comma B comma C and second E comma F comma G. Okay, such a element from our group. So and then prove that it is a commutative. Okay, so again you may go for Zn cross Z, Zi cross Zi, again Zni cross Z cross singleton 0. Okay, so all R gives commutative ring. Okay, you may have to try for your homework and let me know in a comment section how it is. Okay, is it difficult to solve or not? Okay, so I will come up with the another video depending on these examples. Okay, so this one is quite much easier to understand. Okay, and this is only here for the definition of a commutative ring. Okay, I hope so you all have understood definition for commutative ring. Okay, now we'll move for the next definition, which is a Boolean ring. So what the definition of a Boolean ring says that when we have ring R under addition dot is said to be a Boolean ring. Okay, so as we learn in a Boolean group, okay, so it is a Boolean element. It says that when we take element and its square, both are coming equal. So similarly, it is here in a ring. Here only the difference here we have two operation, addition and multiplication. Okay, under ring. So under ring, if Boolean ring satisfy A square which is equal to A. Okay, so this is the definition for Boolean ring and all A from the ring. Okay, so A square which is equal to A, like under Z5. So A square, for your understanding, we can write under Z5 we take any element from Z5 like a 5. Okay, if I consider any element from Z5 which is a 5, and if I take square from this 5, so it comes to 25. Okay, under Z5 the 5 means 0 here. Okay, 5 means 0 element here. So I wanted to explain to you all here what is the Boolean element look like. Okay, so if I consider Z5 which is a 5 which is equal to 0, okay, and 5 can be written as 5 which is equal to 5 square. Okay, 5 square is a 25, and 25 under Z5 again, which is a 5 means equal to 0. That means A square which is equal to A, 5 square which is equal to 5 means 0. It gives us the original element, so we call it as the Boolean element. Okay, so we have to look at through whole ring. Okay, so if we wanted to consider for ring, so we have to check for each and every element from our ring. So if I consider, so here it is my second example, ring as a Z2. So I consider here under Z2 we have only two elements, 0 and 1. Now let's verify whether this ring is a Boolean ring or not. Okay, so Boolean ring means we have to take any element from our ring and we have to show its square which is equal to actual element. Okay, now if I consider first element 0, so 0 square always gives us 0. That means A square which is equal to A, and 1 means 1 square which is equal to 1. That means both the element hold the property A square which is equal to A, and all A belongs to Z2. Then we say that Z2 which is a Boolean ring. Okay, so how easy that topic is, we just have to apply the definition from Boolean ring. Okay, now let's get to the another example. So we want the example of a Boolean ring which order is 4 and infinity. Okay, so now think about it, which is the example possible for the Boolean ring which gives the order, group of order is a 4 and infinity. Okay, now here we can see I taken here Z2 cross Z2. Okay, Z2 cross Z2 as a group here, Z2 cross Z2, and the element from our group which look like Z2 contains 0 1, and again Z2 contains 0 1. Take their possible chances, we will get the 0 0 0 1 1 0 1 1. Okay, so how many elements are there? Total number of 4 elements. So it shows that Z2 cross Z2 is having order 4. Okay, and one more condition. So we have to show whether Z2 cross Z2 or Z2 cross Z2 cross Z2 having element of order infinity or not. Okay, so first element we will see here a square which is equal to a need to be there. Okay, then we say that it is a Boolean ring. So 0 into 0 comma 0 bracket square always comes 0, 0 comma 1 bracket square. So we taken as 0 comma 1, it always goes to 0 1. Okay, so how we find 0 comma 1 square? That we just have to take the cross product of these two elements. Okay, so it is easier to find. It's 0 square 0 0 square, it is a 0 0 0 1 square, it remains 0 1 into 0 1, always it gives us a 0 1. Okay, and again 1 0, it gives us a 1 0. Okay, because 1 it is element there, and if you multiply any order pair to this element, it always gives actual value. Okay, so 1 into 1 bracket square, it always gives us a 1. Okay, so a square means a square which is equal to a, it gives us Boolean ring. Okay, so Z2 cross Z2 is a Boolean ring, and which is having 4 elements, first, second, third, fourth. Already I explained how. So all are 4 elements from our Z2 cross Z2. So that's why our order of a ring which is a 4. Okay, order of ring is a 4. Now we want the ring which is a Boolean ring, but its order need to be a infinity. So which is a possible? Z2 cross Z2 is a Boolean ring. So if we take Z2 cross Z2 cross Z2 3 times Z2, so it always gives us Boolean ring. Again, if you go for Z2 cross 10 times Z2, it always gives us Boolean ring. But what if I consider Z2 cross Z2 cross Z2 up to so on? Okay, that means infinite element Z2 I consider here. Okay, so I consider here infinite times Z2. So it is quite difficult to find out whether it is Boolean ring or order of a ring. But as we saw earlier, okay, that gives Z2 cross Z2 cross Z2 as a Boolean ring, and it is having order for 2 Z2 cross Z2 is a 4. Okay, so if we go for infinite element, it gives us a Boolean ring, and which order is infinity. Okay, so these are uncountable, Z2 cross Z2 cross Z2. That's why its order is infinity, and the group is Z2 cross Z2 is a Boolean ring of order infinity. Okay, so that's it for our today's lecture. I just wanted to explain to you all here the Boolean ring and commutative ring. Okay, so these are the basic definition from ring theory, but it is very much important to solve a different type of the example from net set gate. Okay, so I hope so you all have understood my today's lecture. It is nothing is difficult here. So if you found anything difficult, let me know in the comment section. I will come up with some other videos. Okay, so thank you everyone. Thank you for my today's lecture.